Measurement System Analysis, or MSA, is a critical process used to evaluate the quality of a measurement system. It helps us understand how much variation in our measurements comes from the measurement system itself, rather than the actual process we're measuring. This is essential for making sound decisions based on data. Without a reliable measurement system, we risk making incorrect conclusions and implementing ineffective solutions. Imagine trying to bake a cake with a faulty oven thermometer. You might think the oven is at the correct temperature, but the cake could be undercooked or burnt. Similarly, a flawed measurement system can lead to inaccurate assessments of product quality, process performance, and customer satisfaction. MSA helps us avoid these pitfalls by providing a structured approach to evaluating and improving measurement systems. It is particularly important in industries with strict quality requirements, such as manufacturing, healthcare, and aerospace. In these sectors, even small measurement errors can have significant consequences. By implementing MSA, organizations can ensure that their measurement systems are capable of providing reliable data, which is essential for making informed decisions about product design, process control, and continuous improvement. MSA involves a series of studies and statistical analyses designed to assess the various components of measurement error. These studies help us quantify the impact of different sources of variation, such as the instrument itself, the operator using the instrument, and the environment in which the measurements are taken. By understanding these sources of variation, we can take steps to minimize their impact and improve the overall accuracy and precision of our measurements. Accurate measurement is the cornerstone of effective quality control and process improvement. Without reliable data, it's impossible to identify areas for improvement or track the effectiveness of implemented changes. Imagine a doctor trying to diagnose a patient with a faulty blood pressure monitor. The diagnosis could be completely wrong, leading to inappropriate treatment. In manufacturing, accurate measurements are essential for ensuring that products meet specifications and customer requirements. If the measurements used to assess product dimensions are inaccurate, the final product may be defective or unusable. This can lead to customer dissatisfaction, product recalls, and significant financial losses. Accurate measurement also plays a vital role in process optimization. By accurately measuring process parameters such as temperature, pressure, and flow rate, we can identify opportunities to improve efficiency and reduce waste. This can lead to cost savings, improved product quality, and increased customer satisfaction. Furthermore, accurate measurement is crucial for monitoring the effectiveness of process improvement initiatives. Without reliable data, it's impossible to determine whether the implemented changes are having the desired effect. Accurate measurement provides the feedback necessary to adjust and refine improvement efforts, ensuring that they deliver the desired results. In essence, accurate measurement is the foundation upon which effective quality management is built. Precision in measurement refers to the consistency of results obtained when repeated measurements are taken under the same conditions. It's about how close the measurements are to each other, regardless of whether they are close to the true value. Two key components of precision are repeatability and reproducibility. Repeatability refers to the variation observed when the same operator measures the same item multiple times using the same instrument. High repeatability indicates that the measurement system is consistent within the same operator. Reproducibility, on the other hand, refers to the variation observed when different operators measure the same item using the same instrument. High reproducibility indicates that the measurement system is consistent across different operators. Think of shooting arrows at a target. If all the arrows cluster tightly together but are far from the bullseye, the shots are precise but not accurate. This scenario represents high repeatability and reproducibility, but low accuracy. Conversely, if the arrows are scattered all over the target but their average position is close to the bullseye, the shots are accurate but not precise. This represents low repeatability and reproducibility but high accuracy. The ideal scenario is to have both high precision and high accuracy, where the arrows cluster tightly together at the bullseye. This is the goal of any effective measurement system. Understanding and quantifying both repeatability and reproducibility are crucial for assessing the overall precision of a measurement system. Accuracy in measurement refers to how close a measured value is to the true value. It's about hitting the bullseye, not just clustering the arrows together. Several factors contribute to accuracy, including stability, linearity, resolution, and bias. Stability refers to the consistency of measurements over time. A stable measurement system produces consistent results, even when measurements are taken at different times. Linearity refers to the consistency of measurements across the operating range of the measuring instrument. A linear measurement system produces consistent results, regardless of the magnitude of the measured value. Resolution is the smallest increment that the measuring instrument can detect. A high-resolution instrument can detect small changes in the measured value. Bias, on the other hand, is the systematic difference between the measured value and the true value. A biased measurement system consistently overestimates or underestimates the true value. Imagine a scale that always reads 2 pounds heavier than the actual weight. This scale is biased. Assessing and minimizing bias is essential for ensuring accurate measurements. Understanding these 4 components of accuracy, stability, linearity, resolution, and bias is crucial for evaluating and improving the overall accuracy of a measurement system. By addressing each of these factors, we can ensure that our measurements are as close to the true value as possible. Section 5, Calculating Key Metrics, DPU, DPPM, DPMO, and RTY. Several key metrics are used to assess process quality and performance. These include defects per unit, or DPU, defects per million opportunities, or DPMO, defects per million, or DPPM, and rolled throughput yield, or RTY. DPU is a simple measure of the average number of defects found per unit. It's calculated by dividing the total number of defects by the total number of units inspected. DPPM is a similar metric that expresses the number of defects per million units. It's calculated by multiplying DPU by 1 million. DPMO takes into account the number of opportunities for defects per unit. It's calculated by dividing the total number of defects by the total number of defect opportunities and then multiplying by 1 million. RTY is a measure of the overall process yield, taking into account the yield of each individual step in the process. It's calculated by multiplying the yields of each step together. These metrics provide valuable insights into process performance and can be used to identify areas for improvement. For example, a high DPU or DPMO indicates a process with a high defect rate, suggesting the need for corrective action. By tracking these metrics over time, we can monitor the effectiveness of process improvement initiatives and ensure that they are delivering the desired results. Understanding and calculating these metrics is essential for any quality professional. Section 6. A practical example, telecom service provider defects. Let's consider a real-world example of how these metrics can be applied. Imagine a telecom service provider that wants to assess the quality of its customer service process. They collect data on the number of defects or customer complaints per 100 calls. Suppose they find a total of 25 defects in 100 calls. The DPU would be 25 divided by 100, which equals 0.25. The DPPM would be 0.25 times 1 million, equaling 250,000. If each call has 5 opportunities for defects, such as billing accuracy, call clarity, connection speed, customer service representatives' helpfulness, and resolution time, the total number of defect opportunities would be 100 calls times 5 opportunities per call, equaling 500. The DPMO would be 25 divided by 500, then multiplied by 1 million, resulting in 50,000. This example illustrates how DPU, DPPM, and DPMO can be calculated and used to assess process quality. By tracking these metrics over time, the telecom provider can monitor the effectiveness of its customer service improvement initiatives and ensure that they are delivering the desired results. Furthermore, by analyzing the types of defects that occur most frequently, the provider can identify specific areas for improvement within the customer service process. This targeted approach can lead to more effective solutions and greater customer satisfaction. Section 7. Cycle time and lead time, measuring process efficiency. Cycle time and lead time are 2 important metrics used to measure process efficiency. Cycle time is the time it takes to complete a single task or process step, while lead time is the total time it takes from the initiation of a request to its completion. Understanding these metrics is crucial for identifying bottlenecks and streamlining processes. A short cycle time indicates a highly efficient process, while a long cycle time suggests potential areas for improvement. Similarly, a short lead time indicates a responsive and customer-focused process, while a long lead time can lead to customer dissatisfaction and lost business. Imagine ordering a product online. The lead time is the time it takes from when you place the order to when you receive the product. The cycle time for each step in the process, such as order processing, picking, packing, and shipping, contributes to the overall lead time. By measuring and analyzing cycle time and lead time, organizations can identify areas where processes can be streamlined and made more efficient. This can lead to reduced costs, improved productivity, and increased customer satisfaction. For example, if the cycle time for a particular manufacturing step is excessively long, the organization can investigate the cause of the delay and implement solutions to reduce the time required. This could involve automating the step, improving the layout of the workstation, or providing additional training to the operators. Section 8. The role of MSA in process improvement. MSA plays a crucial role in process improvement initiatives. By ensuring the accuracy and precision of measurements, MSA provides a solid foundation for data-driven decision-making. Without reliable data, it's impossible to identify areas for improvement or track the effectiveness of implemented changes. MSA helps us separate the variation due to the measurement system from the variation due to the process itself. This is essential for accurately assessing process capability and identifying the true sources of variation. Imagine trying to improve the accuracy of a dart thrower while using a warped dartboard. The warped dartboard introduces additional variation, making it difficult to assess the dart thrower's true skill and identify areas for improvement. Similarly, a flawed measurement system can mask the true performance of a process, leading to ineffective improvement efforts. By implementing MSA, organizations can ensure that their measurement systems are capable of providing reliable data, which is essential for making informed decisions about process improvement. MSA helps us identify and minimize measurement error, allowing us to focus on improving the actual process. This leads to more effective solutions, faster improvement cycles, and greater return on investment. Section 9. Implementing MSA. A step-by-step guide. Implementing MSA involves a systematic approach to evaluating and improving measurement systems. The first step is to define the measurement system and its intended use. This includes identifying the specific characteristics to be measured, the range of measurements, and the required accuracy and precision. Next, a gauge R&R study is conducted to assess the repeatability and reproducibility of the measurement system. This involves having multiple operators measure the same items multiple times and analyzing the resulting data. The results of the gauge R&R study are used to determine whether the measurement system is capable of meeting the required accuracy and precision. If the measurement system is found to be inadequate, corrective actions are taken to improve its performance. This could involve recalibrating the instrument, providing additional training to the operators, or improving the measurement environment. Once the measurement system is deemed acceptable, ongoing monitoring is essential to ensure that it continues to perform as expected. This involves regularly checking the calibration of the instrument and conducting periodic gauge R&R studies. By following these steps, organizations can implement a robust MSA program that ensures the accuracy and precision of their measurements, providing a solid foundation for quality control and process improvement initiatives. Section 10. Benefits of effective MSA implementation. Effective MSA implementation offers numerous benefits for organizations. By ensuring the accuracy and precision of measurements, MSA enables data-driven decision-making, leading to more effective quality control and process improvement initiatives. Accurate measurements allow organizations to identify areas for improvement, track the effectiveness of implemented changes, and make informed decisions about product design and process control. This leads to improved product quality, reduced costs, and increased customer satisfaction. Furthermore, effective MSA implementation can improve communication and collaboration within the organization. By providing a common language and framework for discussing measurement systems, MSA facilitates clear communication between different departments and stakeholders. This fosters a culture of data-driven decision-making and continuous improvement. MSA can also enhance an organization's reputation for quality. By demonstrating a commitment to accurate and reliable measurement, organizations can build trust with customers and stakeholders, solidifying their position as a leader in their industry. In addition, effective MSA implementation can help organizations comply with regulatory requirements and industry standards, avoiding potential penalties and legal issues. Overall, effective MSA implementation is a strategic investment that delivers significant value to organizations across a wide range of industries. Section 11. Conclusion. The power of accurate measurement. In conclusion, accurate measurement is the foundation of effective quality control and process improvement. Measurement System Analysis, MSA, provides a structured approach to evaluating and improving measurement systems, ensuring that the data we collect is reliable and meaningful. By understanding the concepts of precision and accuracy, and by calculating key metrics like DPU, DPPM, DPMO, and RTY, we can gain valuable insights into process performance and identify areas for improvement. MSA empowers us to make data-driven decisions, leading to more effective solutions and greater return on investment. Implementing MSA is a strategic investment that delivers significant benefits, including improved product quality, reduced costs, increased customer satisfaction, and enhanced organizational reputation. In today's competitive landscape, organizations that prioritize accurate measurement and effective MSA implementation are well positioned for success. They can confidently make informed decisions, drive continuous improvement, and achieve their quality objectives. By embracing the power of accurate measurement, organizations can unlock their full potential and achieve sustainable growth. MSA is not just a technical process, it's a fundamental principle that underpins quality excellence.